Good morning everyone, I'm Terje, and today I will show you or give an introduction to nonlinear geometry behavior in NX SOL 601. And I will use an example from the NAFEM's book, Introduction to Nonlinear Finite Element Analysis. And this is my example. It's a rigid link connected to ground by a spring, torsional spring. And when you apply a load at the end, this one will deflect and you will have an angle theta here. And for small angles, you can run linear analysis and solve it analytically. For larger angles, you have to use a nonlinear formulation. And I will show you how to do it in NX. This will be the last of 3 introduction videos in nonlinear finite element analysis. The first one focused on materials, nonlinear material behavior. The next one focused on nonlinear contacts, and this one will focus on nonlinear geometry. And this is really a huge area covering lots of issues. I have previously released videos on snap-through and snapback, where you have to apply arc length methods and more sophisticated algorithms. In this video, I will simply use, it's not going to be a singular in any position, so I simply add incrementally a conservative and a follower load at the end. So here I will demonstrate large displacements and follower and conservative loads. This is the NAFEM's model, and it will demonstrate large rotations and displacements. I will have no contacts or plasticity in this model. I will demonstrate linear versus nonlinear analysis, and I will also demonstrate conservative and non-conservative loads. Non-conservative loads are also called follower loads. For this model, you can simply estimate the torque or moment in the hinge here. It's equal to P, which is the load, which is conservative in this respect, multiplied with L times cosine of theta. That is the arm. And this torque will be equal to the stiffness times the angle theta. You can reformulate this one and you can write it like this. You divide by the stiffness and then you got PL over K, which we will plot, is equals to theta over cosine theta. And as you know, when the angle is small, theta is small, cosine theta can be replaced by 1. It's almost 1. And then you can say that PL over K is theta. That means a linear relationship, while this one, for larger angles, represents a nonlinear relationship for the equation describing the equilibrium of forces. So geometric nonlinear effects need to be simulated when stiffness properties or loads change significantly as the result of deformation. This is my NX interpretation of the NAFEM's model. First, I created a bar which was 10 centimeters or 100 millimeters long with a cross section of 10 by 10 millimeter. And then I meshed it with the hex 20 elements with a size of 5 millimeter. Then I made another part which has an offset of 10 millimeters from this bar. There's a 10 millimeters gap here. And then I made another part, which is mainly made for visualization purposes. Then I applied a rigid material, a steel material of both parts, with the E modulus of 200 gigapascal, Poisson of 0.3. And as you can see here, first I meshed both parts with hex elements. Then I applied one RB2 element, which is connecting a node here to this surface of this part. And then I made another RB2 element, which is connected to the bar, with a master node in the same location. So here I have 2 master nodes, which are coincident. And then I added a C-bush element here between the 2 coincident master nodes. And then I needed to define a local coordinate system in order to define the directions of the C-bush element. So that's pretty much my model. Here are my loads and boundary conditions. First, I applied a fixed constraint as shown below. I've constrained this face here on this part. Then I applied a conservative force in 1000 increments during 10 seconds at the end of the bar. So here is my load. It's defined like this. I used a force, and then I used a field to define the force, which I will show you later. It starts at 0 and is increased gradually to 100 newtons in negative x direction. That means upwards. And that will give me a positive y angle here, theta. And then I incremented this so that the load is added during 10 seconds. You see it here. What is important here is that I switch on the large displacement option in the case control settings that you do here. Large displacements must be on in this example. I don't need to use large strains because I don't have plasticity. I'm working in the linear region of the materials. So these are my loads and boundary conditions. And I used a conservative load here, and I applied the load in a direction which is given by the fixed minus negative x direction. So it's conservative. And what happens then is that when it has a conservative direction, this will start to rotate, but this bar will never rotate more than 90 degrees, because then the length times the cosine of the angle is approaching 0, and then there is no more torque to be applied here, and then it stops. I will soon show you how to set up and run a large displacement analysis in NX. That means nonlinear geometry. But first let's have a look at the results. This is the initial position, and there is no displacements here. This is the first animation frame. And then we can jump to the last one. And here we can tell that the load that was applied in a conservative direction, that means in the minus x direction, has rotated the rigid beam 82.15 degrees. And then the resistance here in the spring, which has a stiffness of 1000 Newton meters per radians, multiplied by the angle in radians, which is 82 divided by 57 approximately, then that resistant torque or reaction force is balancing the applied moment given by the conservative load. So it stops in this position. And this is a nonlinear analysis and a conservative load, and that means that this bar will never rotate more than this with a given load. And whatever load we use, it will not pass 90 degrees, because then the arm, which is the angle times the length, will approach 0. To visualize the nonlinear geometric effect for this model, I prepared a graph in Excel. Here is the basic equation from the Nathan's book. And it says that PL multiplied by cosine theta gives me the moment in the hinge. And that moment is equal to stiffness times the angle. And I reformulated that relationship so I can plot it like this. So here I have PL over K at the ordinate axis. It's this number. And if we look at the linear relationship, we see that for small angles, cosine theta becomes almost 1. And then PL over K is equals to theta. And if we plot theta in radians, then there is a linear relationship simply here. PL over K becomes directly theta. Then we can see that if we have larger angles, this assumption is not valid. The cosine theta is not 1. So if I instead plot theta over cosine theta, I end up with a graph which is given by the dotted blue line here. And you see that because cosine theta approaches 0, this value goes to infinite. And what that means is that this bar will never be able to rotate more than 90 degrees, because simply the arm, which gives the moment, becomes 0, because the bar will be in the vertical direction. And you can see that until the angle is roughly 0.5 radians, the linear relationship is okay, and you can use a linear analysis. But you also clearly see the nonlinear effect from the geometry change or the large rotations for bigger angles. And that is what we are going to focus on here. So when I run this SOL 601, I simply calculated, or I plotted the reaction torque or moment in the hinge, which is actually PL times cosine theta. And then I divided it by K and by cosine theta in order to get this value here, which I wanted to plot. And then I noticed that the results I got is exactly the same as the nonlinear relationship here. So the nonlinear geometric behavior is captured by the SOL 601 analysis when the nonlinear geometry switch is toggled on. If you want to run this nonlinear geometry analysis yourself, this is how to do it. The model is basically the same as I used in the nonlinear contact analysis. I have this bottom part, which I used to constrain the model. This is more or less like rigid ground. This part is a 10 centimeter or 100 millimeters long bar with the same cross section as earlier mentioned, 10 by 10 millimeters. The mesh is hex 20 elements with size 5 millimeters. And then this end has one RB2 element. Here is one master node connected to this surface. Here is another RB2 connected to that surface. And in the middle there, I have a C-bush element. And let's check out the properties there. I applied an almost infinite stiff constraint or spring in the XY-Z direction, in the same for the rotation about X and Z. But the rotation of the Y-axis is having a value of 1000 Newton millimeters per radians, which gives me the constraint force. So I have to output the torque or moment in the Y rotation for this C-bush element. So that's the setup, and these are the two meshes, as I mentioned. Then we can check out the simulation file, and we can have a look at the boundary conditions. Here you see my constraints are like this. This end is fixed, and then I have a load here, which is applied in that direction. And here you can see I've applied a follower load. But if I want to apply a conservative load, I simply go and use a long vector like this, and I use negative X direction, and I press OK. Then I have a conservative load that always is pointing in the vertical negative X direction, like this. Then in the SOL 601 setup, I have the parameter large displacements toggled on, and that is really important. The large strains can be toggled off because I don't have any kind of plasticity or large strains in this model. Then in the case control, I used a time step interval setting that is slightly different from previous examples. Here I used 1000 time steps, and I used a shorter time increment of 0.01 millimeter because of the large rotations. And that means I have a total simulation time of 10 seconds, as in previous examples for the material nonlinearity and the contact nonlinearity. And I applied this one. Then I used output requests, pretty much the same. I think I just used all the default settings here. I probably asked also for, what is it? It's the, I think it's some reaction forces, SPC forces. No, I was looking for the forces in the C-bush element, but it will automatically be output when you have the reaction force enabled. MPC forces is also enabled, and applied force. Okay. So that's the simulation setup. And now I can run the simulation. When the simulation is completed, I can toggle on the result tab. And here we see for the first increment, we have a total of 1000 increments, and we probably don't want to watch everyone. But let's first check the rotation, the nodal rotation. And we can select the y-axis, which is the active axis. And then we can set up the animation. And we use iterations. And I don't want to see each frame. Let's use a step size of 10 frames, and then we can run the simulation. And here you see the result from the large displacement analysis. And you can see that the angle rotates from 0 to 82 degrees, which is roughly 1.44 radians. So that's the result when you use a conservative load. And you should notice that since the load is always pointing in the vertical upward direction, that means minus x, the bar will never rotate more than 90 degrees, because the arm, which is the length of the beam, multiplied by the cosine of the angle, is going to approach 0. And that means you have no more torque adding to the system. And then the spring will stop to deflect and will stop. So the next thing we can do now is to check the torque. We can select not reaction force, but we have to check the dashpot results. We can use moment about y-axis. We can of course plot it like this, but it's more convenient to graph it. And then we click on this node where the C-brush element is located, and we can plot this one. And here you see what happens. The load is increased as a function of time, but you see there is no linear relationship between the torque and the applied force, because the cosine of the angle approaches 0. That means that if you continuously increase the load, the resulting moment will not increase that much, because the arm is going to almost 0. When you approach 90 degrees, it will be absolutely 0. And then you will add no more torque, and the system will stop. So this is the nonlinear effect. Then I will show the effect of applying a follower load instead of a conservative load that is pointing in the same direction. A follower load is simply a load which adapts to the deformation of the geometry or the FEA model. There are many examples on this which are more sophisticated, like balloons and cables and whatever. But let's have a look on this simple case. First, you have to activate the large displacement option, which is already on in my model. Then we have to use magnitude and direction to enable the modeling of a force 1 or force 2 load. These two options represent follower loads in NX. And then, which is really important, I didn't know about it, so I made it wrong the first time. The node with the applied load must either be the node 1 or node 2. That means G1 or G2 in this example, when using a force 1 to define the follower load. If you have an example like this, let's say a thin shell or a beam element, then you don't have a G1 or G2 node which can define direction. And then you can apply or model a rigid element that is pointing in the load direction. And you can use the two endpoints, the master and slave of the rigid element, as the direction of the follower load. So when you have a large displacement like this, the load will change its direction given by the position of G1 and G2, or node 1 and node 2, which is referred to as in this menu. And what you will see is that the follower load will influence and contribute to a follower stiffness. And I'll show you how to do this. I will just first animate the result, and then you see that now the load will not, or the rotation will not stop at 1.44 radians or 82 degrees. It will actually not stop before 601 degrees is reached. And that's because the applied moment is not reduced by the length of the arm, because the arm length is constant, because the load is always perpendicular to the beam. And now I'll show you how to model it. Here is my model again. Let's have a look at how to change the load from a conservative load to a follower load. Here's my load, and the first thing I've applied is the application point, which is this node. And then let's just have a look at the applied force. At time 0 there is no load, and after 10 seconds I've applied 100 newtons. That's it, and as I previously said, if you apply a constant value here, the load will be instantly applied in the first increment. It will not gradually be added, even if you have a time stepping setup in the case control. So here, in the first example, I had force along vector and applied vertical x direction or negative, and that gives me a conservative load. But if I select force 1, I could also select force 2, but force 1 is more convenient here. And then as node number 1, I select this one. And as node number 2, I select that one. So these are my two nodes, number 1 and number 2. And as I said, it's important that the application node where I apply the force is one of these two. And now I selected node 1 to be the application node, force application node. And now I have a follower load, and the direction of the load will change with the deflection of node number 1 and 2. So the load will always be pointing perpendicular to the beam. Let's now see what the results will be. Now the simulation with the follower load has completed, and we can check the results again. Let's start with checking the rotation about the y-axis of the C-brush element. Let's set up the animation, use iterations, and we skip some time increments, and we start the animation. And here you see what happens. The final rotation is 601 degrees compared to 84 when we only had this conservative load. When we have a follower load, the applied moment will not change because of the angle. It only changes due to the applied load because the load is perpendicular to the beam. So the arm will not change, and hence the moment will increase linearly with the applied load. And that means we will not have equilibrium about this axis before the rotation is 601 degrees. So you can tell that there is a huge difference between running with a conservative load and a follower load when you have large displacements. Let's stop this animation, and then we can just check the applied force. Then we use spring dashpot results. We use the applied moment. And let's graph it instead like this. And here you see the moment is increasing linearly with time or applied force. And that proves the big difference. So now you see that when you use a follower load, that will have an effect of the tangential stiffness. You will actually add some kind of a follower stiffness to the system, which has to be included for large displacements. So that concludes my presentation of nonlinear geometry. You should also note that I have more advanced stuff, which is demonstrating snap-through and snap-back problems, which has more to relations to instability, where I use arc length methods to control the time stepping or the force incrementation and the displacement incrementation when you have limit points and turnaround points. That's more advanced stuff, but these three videos which I created now, the nonlinear materials, the nonlinear contacts, and nonlinear geometry, represents an introduction to different nonlinear finite element analysis effects. I hope you like them.